Welcome back to Differential Calculus. I realized out of order while I was filming that I accidentally left one of the examples out of the video on the power rule, so I want to correct that here. The last topic we have is higher order derivatives. And the idea of a higher order derivative is kind of what it sounds like. If we have a function, f of x, we have its derivative, f prime of x is df dx. Well, what if we decided to start analyzing this function and we took the derivative of that guy? Well, that would be f prime prime of x, which is the derivative of f prime of x. F prime of x itself is df dx. And because you have all of these dx's going on, a common notation for this is d squared f over dx squared. So if I have a function, let's say f of x is x to the fifth minus 27x squared. I can take its derivative using the power rule and the linearity. F prime of x is going to be 5x to the fourth minus 27 times 2 is 54, x to the first power, or just 54x. Then I can take the second derivative, which I'll denote f double prime of x. The derivative of 5x to the fourth is 20x cubed. The derivative of 54x is just 54. If I want to, I can keep going from here. A third derivative, f triple prime of x. The derivative of 20x cubed is 60x squared. The derivative of 54 is 0. And somewhere around here, mathematicians realized that all of these primes would start to get you cross-eyed. So instead of continuing with that, we tend to put a number in parentheses if we want to keep going. So the fourth derivative would be written as f parentheses 4 of x. It comes out as 120. There are a number of examples of how derivatives work. I've kind of shown you the basic idea. If we think about in kinematics, in physics, instead of f of x, we have x of t as our position. Then we could take x prime of t. The change in x over time, change in position over time, is velocity. And the second derivative would be change in velocity over time, which is acceleration. And generally in physics, that's all the further you really go, but if you wanted to, you could keep going. The third derivative, change in acceleration over time, is called the jerk. The fourth derivative, change in jerk over time, is called the snap. Right? You don't think about those often in physics classes, but they do exist. Right? If you are driving a car with a high jerk, that is hitting the accelerator or the brake very quickly. It jerks you around. The name is something you've seen, right? The snap, if you have ever seen or used a whip, you can get a snap where the change in jerk is so fast, it causes ripples in air that are audible. I can't imagine why anyone would want to keep going beyond that, but yes, we can in fact keep going beyond that if we really want to. Change in snap over time is called a crackle. And yes, it actually is true. Change in crackle over time is called a pop. All right, this is not a physics class. You do not need to know this list. You don't need to be able to talk about them. I wanted to give that to you because it's a good visual idea of what's going on. Right? At least the first couple, position, velocity, and acceleration, are things that we can generally think about and experience in our day-to-day lives. If you are studying something other than physics, right, thinking about a graph, thinking about how fast the graph is moving up and down as the velocity of the graph, thinking about how fast that velocity is changing as the acceleration of the graph is a little bit more in line with what we are doing in this course. But I hope that gives you a picture of what's going on, a little bit of notation. Higher order derivatives are a thing. We're going to see some examples later on in the course of where the second derivative is useful. And if I have enough time, there is an example I know of where the fourth derivative is useful. I've never seen any application of any of the higher ones than that. In any event, that's all I have on this video. Thanks as always for joining me. I'll see you next time.